obstacles and future directions. And so let's get started with deep learning. So we are slowly moving away from the so-called expert systems that had varying degrees of clinical utility, and we're moving towards more advanced methods that in some or very few instances are starting to match human level performance. And so ideally in the future, in an ideal scenario, we would like to continue to learn from systems that have superhuman performance. And the main drive behind this shift is really in the underlying methods. So we have moved away from handcrafted engineered features that are combined with more traditional machine learning models, and we've moved towards deep learning or neural networks where the feature definition happens automatically. And just to quickly give you an idea of what happens inside a neural network, imagine we have a classification problem. Very simple here. We have two features to start with, and as you can see from this plot, that these two classes are not linearly separable, so we can't separate them with straight line basically. So let's hypothesize that we need two decision boundaries that will help us classify a newly given data point. So you can actually think of every node inside a neural network as handling one of these decision boundaries. So what we've done is we've taken a complex problem and we've broken it down into smaller parts that we can manage. And that's essentially what happens inside the hidden layers of a neural network. So now, assuming that we know where these decision boundaries need to be, and given a new data point with two features, each node in the neural network, in the hidden layers of the neural network, can now query this new point and tell us if it lies above or underneath the decision boundary. And finally, we have an output layer that takes the inputs from the hidden layer and give us a prediction. Now remember that these decision boundaries are parameterized by a weight, which defines the slope of the line, and the bias, which defines the y-intercept of the line. This is just a simple equation of a straight line. But if really we look under the hood, we'll find that each node is performing a linear operation. It's essentially multiplying the input value of the corresponding weight and adding all these up to a bias value. After that, we have an activation function that is applied to each node. Here, we chose a step function, and step function decides if each node will fire or not. So it's very important here to note that activation functions are very important in neural networks, as they tell us whether the input that a specific node is receiving is relevant for the given problem or it should be ignored. And additionally, activation functions also help us approximate very complex nonlinear relationships in data. So a neural network without activation functions is nothing but a simple regression model. The only problem here is with the step function, it's that we cannot differentiate it. So it either returns a 0 or a 1. And hence, we cannot have the network learn on its own what the optimum values for the parameters are. And this was the case until the mid-80s, until Jeffrey Hinton and colleagues proposed that we replace this step function by other differentiable functions that are continuous. So here, we replace the step function with a sigmoid, but it could really be any other function. And once you do that, it's possible to train the network with gradient descent and backpropagation, which is essentially how the network learns. So here we calculate the gradient, or in more mathematical terms, the partial derivative of our loss function with respect to each parameter in the network. And in this way, we can assign blame for the loss to each parameter. So the larger a gradient is for a parameter, the more blame it gets towards the final loss. And the more blame a parameter has, the more it will be updated. And that is how a neural network learns. Now let's kind of move on to something a bit more image-based. So let's take an image here, and let's treat each pixel in an image as a feature. And so we take the image and we flatten it into a one-dimensional vector, and we use this as input to a network. And since this is a supervised learning scheme, so we also have the correct label for this image, so we know it's a number 7. And we add one hidden layer with its associated parameters, and these are the weights and the biases. And then we apply our activation function. In this case, it's a softmax activation function, which is nothing really but the normalized exponential that gives us a vector whose sum is equal to 1. And this way, we can identify which of the number or the digits from 0 to 9 this network is predicting. And so our loss function here finally will be the cross entropy, which basically compares the network predictions with the true label and gives us a loss value. And finally, we have the optimizer, which is the gradient descent in this case. And as we've seen in the first example, we will calculate the gradient of the loss function with respect to all the parameters and then shift them either up or down accordingly. This entire process is then repeated with another input data and so on and so forth. And this is all great, but you can see here that the 7 is really nicely centered on the image. So for instance, if the 7 was shifted to one corner, you can totally imagine that this will throw off the input to the network, and it will completely throw off the outputs of the network as well. And so this approach is very overly simplistic, and it is not really scalable at all, because now our network needs to learn about 7s that are in one corner, in each corner of the image, and 7s in the middle, and so on and so forth. So clearly we need a different solution, and this is where convolutions really shine. What we need is a way of sharing parameters so that 7s are identified wherever they fall on the image. And this is essentially what a convolutional neural network, which if you consult the literature, is the most popular method for modeling image-based neural networks at the moment, so convolutional neural networks, or CNNs. And it is nothing but a neural network that shares its parameters across space. So to take an example, the weight, this kind of weight sharing happens inside convolution kernels or filters. And these kernels are essentially what the network will learn. So the network learns discriminative features from the input automatically without the need to handcraft them. And so for these 3 kernels that that you see on the screen that the network has learned, we perform a simple element-wise multiplication followed by addition to get the feature maps. And essentially, each feature map is highlighting that specific given feature. So I have a diagonal line going up, a diagonal line going down, and the straight line in this case. And we perform this process over and over and over again. And what happens is that we go from a 2-dimensional image to a kind of a skinnier but a deeper matrix representation. This matrix representation could then be fed into a regular neural network as the ones we've seen earlier, and where basically there is no more weight sharing as it was the case with the convolutions. And because of the nature of the convolutions, usually the input is scaled down slightly at each layer. And to kind of help speed up this scaling down, we introduce pooling layers after the convolutions. And so the final setup looks something like that. We have an input image, we have convolutions in blue, and then we have pooling layers in green. The final pooling layer is then flattened out and passed into a regular neural network or fully connected layers without weight sharing. The convolution and pooling layers, essentially, you can see them as doing the perception. So they're really perceiving what's in the image. And the fully connected layers towards the end of the network are doing more of the cognition or the high-level reasoning. And in fact, these ideas are not entirely new. So, for instance, this effort in 1980 was the Neocognitron, and it was probably the first iteration of a convolutional neural network where the weight sharing was introduced. And I stress here on the title of the paper, pattern recognition unaffected by shift in position. And that's the kind of example with the number 7 that we've discussed earlier. So the Neocognitron was based on the idea of simple and complex cells. So Simple cells basically performed convolutions, and the complex cells performed the pooling. Unfortunately, at that time, there was no hot application, so it didn't really catch on. And it wasn't until the late 90s that Jan LeCun and colleagues came up with LUNET. And LUNET was actually put in use by several banks at that time to recognize handwritten numbers on checks. So there was an application, and this is where it kind of started taking off. In the past, starting from around 2012 and 2013, there has been also another recent revival of AI research, specifically neural networks, and this revival has been mainly fueled by large amounts of data that have become available in the past decade or so, mainly due to our data collection practices, big data, and so on. And then also we realized that GPUs or graphics cards that are able to run embarrassingly parallel computational tasks in computer graphics are actually well suited to train neural networks. So we started utilizing these. And once you have data and once you have processing, you can now go deeper by adding more hidden layers, as we've seen. And you can also introduce more fancier activation functions and tricks to avoid overfitting your models, and so on and so forth. And out of this kind of revival came AlexNet in 2012. This is a seminal paper. I think it was cited over 32,000 times so far. And it's really one of the main reasons why we're here today and talking about this topic. It surprisingly has a similar structure to LUNET, which was its predecessor from 20 years back. They introduced new activation functions. Then they also utilized GPUs or graphics cards to train their networks, so they were able to slash the training time from weeks down to 6 days. Most importantly, they were also able to test their model, train and test their model on a very large data set, thanks to ImageNet. And so ImageNet is an image recognition data set and competition that started in 2010. And the task was to train on 1.2 million images that are labeled with 1,000 classes. These classes are essentially everyday objects, and AlexNet was also able to beat the reigning champion by a very significant margin of around 11% in 2012, and the rest is history, where most of the works after this point started heavily relying on convolutional neural networks, specifically when it comes to tasks related to imaging. Another breakthrough came from DeepMind in 2016. AlphaGo, they called it. It was able to defeat the human champions in the game of Go. And Go is the oldest board game that has been continuously played to present day. And this was very significant because the number of possible moves in the game is around 10 to the power 170. And that is essentially more than the number of atoms in the observable universe, which is around 10 to the power 80. And this is something that was actually predicted to be decades away, to be able to beat human champions in Go. And they came back a year later with AlphaGo Zero. AlphaGo Zero was actually taught by playing against itself, millions of games, and it was essentially able to gain an incredible amount of experience in a very short span of 40 days. And these are all very high-profile studies, DeepMind, owned by Google, and so on. But there's also been an explosion of deep learning applications in multiple areas. And these have been mainly fueled by the availability of open source libraries that are developed by big tech companies. And this is in contrast to the expert systems, where most libraries were proprietary and usually commercial in nature. So these open source implementations and frameworks for performing deep learning studies have really lowered the barrier to entry. You can recreate a state-of-the-art method or network with very few lines of code and test it on your own data. And another contribution to this revival came from transfer learning. So the reason why transfer learning works is actually, it's quite interesting, is because a neural network learns increasingly higher level features. So for instance, the earlier layers in a neural network will learn low-level features such as lines, curves, and shadows, as you can see here. As you move towards the right and you transition towards higher-level recognizable objects throughout the network. And if we look back at these low-level features are essentially shared among images, whether they're images of cats and dogs or actually medical images. And so they can be reused in a way. So this means that we can learn on a very large data set of photographic images and then transfer the knowledge to smaller data sets of, say, data sets of maybe CT images or so on. And you have multiple approaches to perform transfer learning. You can essentially fix the features that you want, and you can fine-tune the remaining on your data set. So you're essentially starting from the weights that the model authors have stopped training at. Another approach would be to randomly initialize the remaining layers. So let's say you might want to change the architecture, or you want to add more layers, or you have different number of classes, and so on and so forth. So that's another approach. And finally, the simplest approach is to use the image, use the network as a feature extractor. So you can essentially extract features from a given image, and you can use these to build more traditional machine learning models, such as support vector machines or random forests or so on. And the reason why I wanted to stress on this is because a good 40 or 50% of studies in the literature, especially when it comes to medical imaging applications or machine learning applications in medical imaging, end up using transfer learning. So it's really a very good place to start, especially when you have a limited amount of data. All right. So let's move on to focus on medical imaging for now. So since the early computer age in the 60s, there's been a growing interest in quantifying data that is obtained through radiographic images. So you're essentially converting images into quantifiable features, and then using these for a variety of purposes. And computer-aided detection and diagnosis have long been studied in the literature, and the FDA here in the US and other regulatory bodies around the world have cleared many software products, as you already know, in the clinic that contain CAD-E and CAD-X, with computer-aided detection, computer-aided diagnosis components. And the major bottleneck has always been reaching clinically acceptable performance. And of course, in addition to controlling reading times, being able to integrate it seamlessly into the clinical workflow, regulatory approval, cost efficiency, and so on and so forth. And so the methodology shift that we touched on earlier, going from more traditional machine learning methods to deep learning, it now means that we've replaced the combination of feature engineering plus traditional machine learning with deep learning models that learn from experience. And so learning from experience, meaning that they are able to identify the relevant features automatically without the need for handcrafting. And so, for instance, for solid tumor, for instance, we used to quantify features including describing shape, intensity, histogram, texture. All these features can now be learned from neural networks without the need for predefinition, and in some cases also without the need for full tumor segmentations or contours. So let's look at some of the kind of more popular applications. So in 2016, they used a convolutional neural network, and they trained it to detect the referable diabetic retinopathy in the fundus photographs. And here we can see the results on two independent validation data sets. So we have the algorithm in black compared to multiple ophthalmologists in colored dots, as we can see here. And another Another approach from last year is a group at Stanford, and last year, actually 2017, 2 years ago, from a group at Stanford, they showed that transfer learning and fine-tuning a neural network can actually lead to expert-level accuracy in classifying skin lesions. So that was also another major breakthrough. Within radiology and up to mid 2017, I would say, we'll find that most efforts have been focused on segmentation and detection tasks when it comes to machine learning applications in medical imaging. And most of them explored modalities that include MR and CT, and a lot of them have also focused on the brain and lung as the most studied sites. And more specifically, within image-based radiology, we find applications in tasks that are already automated but could be optimized. So, for instance, you have reconstruction. So that's a good example of that. You also have applications in areas that still require quite a bit of human input, such as segmentation, for example. So let's very quickly go through these different tasks. And so starting with reconstruction, you're all well aware that image reconstruction is challenging because the analytical knowledge of the exact inverse function doesn't really exist beforehand. So this function needs to be approximated somehow. So what they've done here is they have recast the MR reconstruction process as a data-driven supervised learning task. And this allowed them to map between the sensor and the image and extract this mapping from training data, essentially. And as the authors mentioned, it gives them immunity to noise and reduction in artifacts when compared with the traditional conventional reconstruction methods. And moving on to detection and diagnosis, I want to introduce this data science ball, which was a competition organized by Kaggle in 2017, and it was offering $1 million in prize money. So the teams were invited to detect and diagnose nodules in low-dose lung CT, and they were more specifically they were asked to predict whether a patient will be diagnosed with cancer within 1 year of the scan. So here we have the winning proposal with an AUC of the late 0.8s. And so what they've done here is they first use a detection network that takes as input a 3D volume and proposes suspicious regions in the images at 3 different scales. And finally, for the diagnosis network, they reuse the weights that are learned in the detection network and produce a malignancy probabilities for the top 5 suspicious regions in the image. And another application here also used CNNs for detecting pulmonary tuberculosis in chest X-ray. So they trained the network from scratch, which is the blue and green lines that you see here on the plot. And for a better performance, they use pre-trained models or transfer learning, as we touched on. And these are the brown and orange lines that you see here. And by examining the activations of the network, they are able to tell where the network is looking when making predictions. And in this case, we have opacities in the upper right lobe, as you can tell from the heat map. Moving on to segmentation, fully convolutional networks are very popular with segmentation tasks. So in this case, there are no fully connected layers. And you perform convolutions to downsample the image, and then you upsample it back to its original size. And in this process, you lose some resolution because of the downsampling. And so to retain some of this resolution, they add activations from the previous layers, and they call these skip connections. And these skip connections is what you can see donated by the arrows here. This approach was also later extended to the UNet, which is a very popular medical imaging segmentation network. I urge you to kind of look up as well. And we also have the VNet that also works with 3D volumes. And it combines the UNet architecture with the residual learning. And residual learning is where they introduce shortcut connections that bypass one or more layers. And it's what you can see here in orange as well. And this prevents the network from getting saturated very quickly during training. And essentially, as neural networks get very deep, it becomes very difficult to propagate the error back throughout the entire depth of the network. And so being able to introduce skip connections can really help with that. This is a project from our lab where we try to predict cardiovascular risk. And so here we use a segmentation network to quantify the coronary artery classifications from CT. So we start first by localizing and segmenting the heart, and then we do a coronary calcium segmentation. And we find that we're able to closely match the expert-derived Agassiz score in two independent validation datasets. Maybe a bit more of interest to this group is a recent effort from DeepMind last year in MICAI, which is a popular medical imaging conference. And here, what they do is they segment tumors as well as organs at risk in head and neck patients for radiotherapy planning. And the performance metric that they use also incorporates preset organ-specific margins that are based on clinical tolerances. And for loss function, they also introduce surface-based Dice coefficient as opposed to the conventional volume-based Dice coefficient. So in this way, they're able to quantify if the deviations from the ground truth are localized, which means that they require less human time to fix, or if they happen around the entire circumference of the contour, meaning that they require more time to fix. And this is very interesting because now we can, we're starting to think, we know what the performance, we know that the performance is not up to the clinical standards, but how much time and how much effort is needed to bring it to that level. And moving on to characterization or prognostication, this project is a project from our lab, and it explores deep learning for quantifying radiographic tumor characteristics. And here we try to predict 2-year survival of non-small cell lung cancer patients. The idea is to go from the very coarse stage classification, stages 1 through 4, and their substages, towards a more finer classification of patients, and ideally heading towards precision medicine, or more specifically precision oncology. So in this project, we train end-to-end on patients treated with radiotherapy, and we use transfer learning to train on patients treated with surgery. And in both cases, we are able to show significant survival group stratification. And this, as I mentioned, is really as a means to augment the classification that we have today through TNM staging. And we also benchmark the neural networks against engineered features and the clinical tumor parameters. And we find that deep learning significantly outperforms these in the case of surgery patients. And this is really important because surgery patients are often excluded from traditional radiomics research or any kind of machine learning research, citing as reasoning the fact that you cannot predict a tumor response if it's based on its phenotype, if it is essentially eventually resected and removed surgically. And in contrast to engineered features that are only extracted from within the tumor, deep learning has access to the entire tumor environment. So here we map the attention over the inputs, and we find that areas both within and beyond the tumor have had a significant prognostic signal. And that signal is usually not picked up by more traditional engineered approaches where we're only extracting features from within the tumor volume. And finally, we also have monitoring over time. So monitoring efforts generally use recurrent neural networks. And these are networks that are designed to work with sequences like text, so they are able to retain computations from previous inputs. And so in this longitudinal CT study of lung cancer patients, we try to predict survival from the periodic follow-up scans that are done pre and post radiotherapy. And so for that, we use pre-trained neural network as a feature extractor, as we've seen earlier. These features are then passed into a recurrent neural network. And finally, we have fully connected layers where the prediction is made regarding the response. And so our design also takes into account the clinical reality, where it is often the case that some scans, follow-up scans for some patients might not have been acquired. What we've also done is build multiple networks with different numbers of follow-up scans, and in independent validation, and as expected, we find that the performance was improved with the addition of each follow-up scan. All right, so now moving on to the challenges ahead of us, and arguably the biggest challenge is data. So we are generating massive amounts of data. These are numbers from the US. In the US we have the PACS, and we have similar systems around the world. We generally have DICOM standards. This essentially means that the data, in principle, is very well organized. The only problem is, with more data, there's more noise. So the idea is discerning signal from noise becomes more challenging. And more importantly, having data is one thing, but having curated data is another thing. And most of the data that we have today is not really curated. And curation represents a major bottleneck in developing any kind of machine learning model. And these could be anything from data labeling to annotations to segmentations, or maybe dealing with incomplete data, or just even assembling the right patient cohort. So really, depending on your data type, you might be able to outsource some of these tasks to something like the Amazon Mechanical Turk. But when it comes to medical imaging, you need domain experts, you need expertise, and this means that the process is usually very expensive, very time-consuming, and requires a lot of effort. A lot of effort that is usually comes against clinicians' time spent working with patients. So there's also an ethical aspect there. So data quality and quantity are particularly important in deep learning. So this is a sketch from one of the prominent deep learning researchers. His name is Andrew Ng, and this is one of a sketch from one of his online classes where he compares traditional machine learning with deep learning in terms of scale. And he makes the point that in deep learning networks, the performance tend to improve with more data, while on the other hand, with traditional machine learning, it tends to plateau. This essentially means that we need to create more and more high-quality data. This kind of general lack of curated medical data, is led to a lot of unsupervised learning approaches. And unsupervised learning approaches, when compared to supervised, the ground truth labels are not needed. Although it's very early to kind of gauge the success of these methods. So this specific effort, they use generative adversarial networks, or GANs for short, to generate abnormal MR images with brain tumors, essentially. And you can imagine how generating medical synthetic data can address curation problems. It can also address class imbalance that we always have in the data. And it could also eliminate patient privacy concerns. So this is really early research that we're looking at. You also have supervised learning, where the labels are inferred from the data itself. So in this case, they have a very large unlabeled data set, and they use it to train a network to predict spatial relationships between patches. So for any given two patches, you ask the network to identify where one falls in relation to the other. So this way, they are sort of priming the network in an unsupervised manner where they don't need curated or labeled data. And then they transfer the weights essentially to, in this case, a specific organ segmentation network, where they train on a much smaller labeled data set. And so before we move away from data, let's talk about benchmarking data sets. So in machine learning research, generally, there are a few so-called toy data sets that are used for benchmarking of training and testing performance. So examples of these include the MNIST and the CIFAR-10 or CIFAR-10, as you can see. And these two data sets provide very good benchmarking, and this is something that we desperately need in medical imaging, because we have multiple sites, we have multiple imaging modalities, and it really becomes important to understand if we're actually moving forward with all these studies. And we do have a lot of competitions and large data sets, but we don't have consensus on specific data sets that could be used for benchmarking. In terms of interpretability, although the math that is used to construct a neural network is pretty straightforward, understanding how the output was arrived at is not. So when you have a network with millions and millions of parameters, this explosion in complexity, it makes it very difficult to debug, to isolate the reason behind a specific outcome or a failure, or actually predict when and where these failures would happen. And so deep learning features are nameless. The imaging characteristics that they measure are highly obscure, and this is in sharp contrast to the engineered approaches that we had earlier. And so interpretability is the kind of, you can say, is the Achilles heel of deep learning networks. And even the term interpretability in machine learning, it doesn't really have an agreed upon meaning. Nevertheless, however, it's still in a very active area of research. And here, on this project, they identify class discriminative regions. So basically, the pixels with the most contributions to the given class output. And we can wrap our heads around the concepts of cats and dogs and so on, but with other imaging types and in other cases, it becomes much more difficult. And here, by combining feature visualization, so that's essentially asking what a specific node in a network is looking for, with the attribution, which is essentially how this affects the output of the network, we can start identifying, or learning how the network decides between classes. So generally, interpretability is very active and an active area of research, and it will be very beneficial, specifically for applications in medicine generally. And when it comes to the regulatory aspects, we have to start asking ourselves if we can treat networks in the same way that we treat drugs that have unknown mechanisms of action. So these are drugs that we know are safe and are very effective, but have very little understanding of how they actually work. And in early 2017, we take the FDA here in the US as an example. They started clearing a few deep learning tools on the market. And it's important to note that none of these tools are actually standalone diagnostic tools, as mentioned here, but they are simply assistive, and they require further clinical interpretation from a medical professional. We also need a better understanding of what is ground truth data. This is especially the case with segmentation tasks where there is very large inter-reader and intra-reader variation. We need to ask ourselves, how do we treat the data that has been used to train models? How do we secure these models in the same way that we secure the data? And we also need to address the lifelong learning aspects of these models. And these models, as they're constantly trained and given more and more data, ideally their performance improves, but also how do we continue monitoring this performance and making sure it continues to adhere to our clinical benchmarks. There's also a lot of ethical challenges. So, beyond medicine, for instance, this specific study, exposed how existing commercial face detection algorithms, they can be biased and they can discriminate based on skin color. This is another one where they exposed that the U.S. criminal justice system uses racially biased algorithms that are used to predict recidivism and decide if a specific individual could be released on bail or not. And it's actually not surprising that we're all still seeing problems like this in the medical space. So 2 years ago, in 2017, DeepMind, which is a subsidiary of Google, they failed to comply with data protection laws when they were given access to 1.6 million patient records by the NHS, the National Health Service in the UK. In this case, the data was used without the patient's prior knowledge. And just last month, actually, there were executives from Memorial Sloan Kettering Cancer Center in New York City that were abused, that have actually abused their access privileges to data. So they essentially gave their own for-profit startup exclusive access to data. So we're starting to see issues like that come up. We also have other issues. We have the garbage in, garbage out problem. If your data curation practices and inclusion criteria are biased by nature, we really need to think what it means when these models that we develop are built on data and is deployed in the clinic. You could also have unethical algorithms by design. So, for example, a good example for that would be the Volkswagen emission control algorithm that I'm sure many of you have heard of. And we might also exacerbate the already existing tension between providing healthcare and making money. So this is especially true since those that are developing and selling automated systems for the clinic and those that are providing care are distinctively two different groups. We also need to guard against learned helplessness. So this is where clinicians become so reliant on automation that they end up abandoning common sense. And finally, these systems might also challenge the dynamics of responsibility in the doctor-patient relationship, and as well as the expectation of confidentiality. So these are things that ethical issues that should be considered as we move forward. And finally, we have security. So many of these deep learning applications are cloud-based, meaning that the processing is sometimes happening beyond the hospital firewall, which makes it highly susceptible to attacks. So how can we sometimes how can the sometimes outdated healthcare IT systems accommodate the kind of relatively more advanced cloud-based solutions without undermining patient privacy concerns, HIPAA compliance, and the like. And luckily, also security is a very active security of machine learning or deep learning specifically is a very active area of research. So in this specific example, you have a local copy of the model within your firewall where you run your inference and training on your local data. And actually, only the updates to the model are sent to the cloud. And then they are averaged across all other users, and you get back a new version of the model, an updated version of the model. And this essentially means that the data never leaves your system. And there are also other approaches, including cryptonets, where you're combining homomorphic encryption with neural networks. So you run your inference on encrypted data, and you also send back encrypted predictions. And these predictions can only be decrypted by the source of the data. And so to very quickly conclude this talk, we are taking steps in the right direction. speed, the resolution, the accuracy, and the sensitivity of imaging hardware has been continuously on improving. And so what we need now is image processing methods that are on par with the sophistication of the imaging instruments. And we also need to capitalize on these high quality images through predictive modeling. And this is on the path to kind of improve the efficiency and the efficacy of patient care. And while we do so, especially in research, we also need to ensure reproducibility. So reproducibility is not something new in science generally, but at the speed at which new applications are coming out, we have to be very cognizant and very careful about the ability to replicate studies. So two projects that we're involved in our lab around reproducibility. This first one is PyRadiomics, and it's an open source Python package. And what it does is it offers standardized algorithm definitions for the extraction of radiomic features from medical images. And the second one is Modelhub. Modelhub is essentially a software dissemination platform for researchers to share fully reproducible and portable implementations of their deep learning efforts. And so we work with authors, we package their models for out-of-the-box replicability and benchmarking. And we should also be very careful with hype. So Amara's law states that we tend to overstate the effect of technology in the short run and underestimate it in the long run. All the applications that we've seen so far, they fall under the band of narrow AI, meaning that AI or artificial intelligence that is able to perform one task and one task only. And we should also be very careful with projections, because the current AI that we have now is unlike human intelligence in many ways. And so excelling in one task does not mean excelling in other tasks. And finally, I believe the role of radiologists, medical practitioners, physicists, medical physicists, and so on will generally continue to expand as they become more connected to technology. And so medical professionals or radiologists specifically, they do more than just interpret images. They're really critical for the AI training process, data curation, validation, and so on. And at the end of the day, productivity drives demand. So if we improve the radiology workflow, we'll definitely see an increase in demand for medical imaging. Thank you very much.
Wow. Thank you very much, Dr. Hosny.
Thank you very much.
Yeah. So we're opening room for questions, please. All right. You could unmute and ask your questions, or you just type it.
Good evening, Dr. Hosny.
Yeah.
Can I go ahead?
Yes, sure. Yeah.
All right. Now, I want to thank him for giving us this great insight into artificial intelligence, and especially how it is applicable to radiology and radiotherapy. But my own question is this. Fine. We've watched a lot of movies, and those movies over the year have formed our perception of what artificial intelligence is like, and how one supposedly bought there and then is going to take over the world and start pitching machine against human. But at least with current trends, current articles, at least we've been able to understand the distinction between narrow narrow intelligence and artificial general intelligence. All right, there and then, for most of us in developing countries, we have interest in AI, but unfortunately we are stuck in the sense that the three basic requirements needed for taking on to build an artificial intelligence model, which is the first one being the expertise, the knowledge base of programming, then data sets, and then processors, all those high-end GPUs. Now, coming from all these challenges, what do you think that with the current resources, limited resources that we have, what do you think we can do to to gather more proficiency in becoming experts in modeling artificial intelligence, particularly how it adapts to our home field, which is radiology and radiotherapy. Thank you.
Yeah, thank you very much for your question. I think first of all we need to ask ourselves, you know, when it comes to low and middle income countries, you know, I'm from Egypt myself, so I completely understand where you're coming from. I think one needs to first understand if you are in control of resources, and you should ask if it actually makes sense to be investing in AI resources. On the other side, you know, you might have someone, the counter argument for that would be, you know, if you have a bunch of money, you better invest in surgeries or invest in medical imaging infrastructure as opposed to in AI ventures. So that's kind of the first part of it. The second part of it, I think generally, in order to push in that direction, in low and middle income countries, you need very good data curation practices. So that's ensuring essentially that data is collected and there are collection practices that adhere to certain standards, and this really will help spearhead your or accelerate your any kind of AI development in the future. And from our experience in the lab, the data curation is really something like 70% of the effort. So you can imagine how valuable that is. In terms of resources, other resources that pertain to technical knowledge, once you have the data, it's actually highly accessible. There are online courses that I'm happy to share with the class that are extremely beneficial, that are free of charge, and that really can give you a tremendous amount of knowledge and know-how in a few months' time. And so that technical aspect is actually, I think, one of the easier problems to tackle, given that you're driven, you know a specific problem that you face in the clinic. You can go online, you can learn a few tips and tricks, and assuming you have data curated, then you can essentially run small experiments. And I think by combining these, you're able to tackle context-specific problems, that the developed countries don't necessarily have.
Wow. Thank you very much for that. So I wanted you, Hosny, please, could you differentiate machine learning from artificial intelligence and from deep learning? What's the difference between machine learning, artificial intelligence, and deep learning?
Sure. Thank you. It's a good question. It's I mean, there's a lot. It's kind of all these buzzwords that you read, and they're kind of thrown around. So artificial intelligence is the umbrella term, and this term was coined in I think it was 1956, so not a very long time ago. And it really encompasses systems that can think like humans. So you can think of it in a very broad term. Now, within artificial intelligence, you have machine learning. So you can imagine, AI and then machine learning as a smaller subset of artificial intelligence. And machine learning, again, it rose to prominence in I would say starting in the mid 80s. With kind of traditional methods that were developed, and in this case, the idea was focused on supervised learning, where you have data, and you engineer features. So, for instance, you can come and say, brain tumors. Around brain tumor, you bring expert knowledge into this. So you say, like, around brain tumor that has is less spiky, let's say, is more likely to be benign, and brain tumor that is infiltrated is more likely to be malignant. So that's expert knowledge, and then you decode this expert knowledge into a bunch of equations that then extract features from images, and then make a prediction or an inference. So now the other within AI, machine learning, and then right next to machine learning, then you have deep learning. And deep learning, as we discussed, is essentially being able to learn these discriminative features without human input. So we don't need to bring in experts. We don't need to write a bunch of equations. The neural network in deep learning approach essentially learns these discriminative features automatically. And so this removes a lot of the guesswork, number one. And at the same time, it allows, you can argue with this, but it allows a much better understanding of the data space, because our experts at the end of the day might also have a bias, and our understanding of the problem might actually not be complete. So we leave the job to deep learning to decipher these features. But at the same time, also, as we discussed, interpretability is a huge problem, because we're sometimes unable to identify why the network arrived at a specific prediction.
Wow, thank you very much. Any more questions, please?
Yes, thank you very much for the extensive discussion on machine learning. Now, from the developing countries, which area do you think we can start now? Because we shouldn't just be left behind like that. I think it's time for us to be involved in some of these advances that is coming on. Because I think there is need for some of our samples or some of our images or some features from our own population to be incorporated into what is going on, so that we could actually see how functional it could be. Now, we know that machine learning, if applied in some simple things, maybe like in diagnosis or in being able to have a uniformity, will be very helpful, because for us, most of our physicians or like pathology radiologists, they are practicing alone. So sometimes they could need this machine learning to assist them in some difficult or some very not clear instances. If they could get some of the machine learning outputs to compare what they see, they should be able to at least feel much more confident. And then sometimes we always have this issue of differences within different physicians, pathologists, radiologists, interpreting the same image. So if machine learning could actually be developed to such a extent that it could give us maybe a uniform interpretation, it should be nice. So I feel we in this part of the world should be able to key in as early as possible, so as to be able to follow up with the advances. So which simple areas do you think we can be involved now based on our own situations?
Yeah, thank you very much. I think generally it might be best to actually build upon some of the technologies that have been developed in developed countries. So, for instance, a task like tumor segmentation for radiotherapy. This is just one example. Something like this, as you mentioned, it has a lot of variation among clinicians, and it is probably likely that anatomical differences between populations might or might not affect the accuracy of a model that is developed, say, in Europe or the US, and being applied somewhere in Asia or in Africa. So I think the first comes to identifying specific problems that might be faced. But also this is focused more on the clinical aspects. For instance, I know that a radiation oncologist can be working on multiple sites. A radiation oncologist somewhere in a low or middle income country can be working on multiple anatomical sites at the same time, and this doesn't allow them, because you're constantly shifting your scope of services, it doesn't really allow them to build expertise in, say, lung or head and neck, or like specific anatomical sites. So having, for instance, a segmentation algorithm or a contouring algorithm that gives hints into how the outputs should look like could really help specifically in situations where you're understaffed. This is within the clinic, but I think also you could also have very low-cost diagnostic tools, which are operated by health workers or maybe by patients themselves. So we looked at the cancer diagnosis system paper, and something like this could be running on a very simple mobile phone that helps patients, gives patients the power into their own health in a way. Or maybe, for instance, there are also tools to analyze peripheral blood samples to diagnose malaria, for instance. So this is more on the patient side, or more on the health worker side. And then we've also discussed applications in the hospital settings with radiotherapy as an example. And the third and final group is more on the meta level. So, for instance, you can imagine, you can have AI-powered analysis of aerial photographs and maybe also weather patterns, and these can help us identify hotspots for disease outbreaks. In areas that are rural areas that are not mapped. And at the same time, you can use AI to or machine learning to plan and optimize the community health workers' household visits. And these, could help with so many things, including reducing neonatal mortalities and so on and so forth. So I believe that the problems in low and middle income countries differ quite a bit than those in developed countries. Here, a lot of the applications are focused on reducing reading times, reducing false positives, because there is a up and running hospital system. So they also want an insurance system. So they want to also reduce fraud. So they want to be able to detect fraud and streamline the claims process for insurance and so on. And these are all non-transferable to low and middle income countries. Whereas, however, a task like tumor segmentation is something that is very time consuming and could potentially be ported straight away.
Okay, thank you.
Thank you.
Thank you very much. Just to say, I know I said this before in one of our classes, we'll be hosting something that has to do with technology, perhaps in the summer of this year. So we'll be having a course, a brief course, not like this one that is just sort of continuous, but a brief course on, and we'll be having faculties from Harvard, from University of Heidelberg in Germany, and from ICT University, for those of us who attended Victor Baraka's class. And we'll be having courses on information and communication technology, and then artificial intelligence as well. So just to keep us informed with that. Thank you very much, Dr. Hosny. Do we have any other questions? Okay. Thank you very much. Just in case you want to contact Dr. Hosny, you can contact me and I'll link all of you up. I think so. All right.
Nice.
With this, we come to the end. With this, we come to the end of the class. We really appreciate you, Dr. Hosny.
Thank you very much for your time. I hope it was helpful.
Yeah. Thank you.
Thank you very much.
Thank you, guys.
Bye.